We're in the process of meeting all of these new standard collections. We've already seen vector, but we're in the process of meeting list, set, and unordered set. And we're going to spend time focusing on each one of those in separate videos. What I want to do at the very beginning, though, is show them all off in one program. I want to show off their similarities. We saw in the previous video that all of them are sort of a way of implementing the abstraction of a collection, a bunch of elements that we're storing. And which one we choose, so whether we choose list or vector or set, depends on what exactly we want the collection to do. What I want to show off before I talk about their differences is their similarities. The fact that using this sort of abstraction viewpoint, so viewing them as all special cases of a general collection, in C++ translates to being able to use very similar notation for all of them. So I'll compile this code just to make sure it compiles. You'll notice what I have here, I've included list and set and unordered set and vector. And so we have a separate header for each of them. So of course, make sure you include the one you need when you use one of these things. In the event that you ever need to use multiset, you would include set. So this set includes std multiset as well. We'll talk about that briefly in a future video. As I mentioned previously, a multiset isn't really a big deal. It's just a question of whether we allow duplicates or not. And similarly, if you want an unordered multiset, you just include unordered set. Okay, so first, list. So recall that std list is an encapsulated form of a linked list. Now, we might remember from 111 that we really would rather avoid the bookkeeping associated with adding and removing linked list nodes. And we can avoid that with std list. So because it's encapsulated, all we have to worry about is telling the list, insert this element, remove this element, or iterate over it, or whatever. You don't have to worry about actually chaining together individual elements of the list. So here I create the list, std list. Its element type is string, just like how I would create a vector. I add two elements, and then I try out some different operations. So a list supports push back, and a list supports a new one called push front. We saw that unlike a vector, I can insert quickly into a list anywhere I want. And so the list provides various ways of inserting elements, including this convenience function push front, which adds at the very beginning. Something that a vector doesn't allow. Although a vector does provide functions to insert stuff anywhere, it doesn't provide any convenient ones because it's trying to hint to you that maybe a vector isn't the best choice for that. So a vector does not have push front. And then I loop over my list using a for each loop, just like I would with a vector. Okay, what's next? How about a set? So a set, recall, is a way of storing a collection of elements where the ordering of the elements is not under your control. So the elements are forced to be in the ascending order of the underlying type. Now, the ordering defined for strings is what you might think of as alphabetical order, so dictionary ordering. Formally, it's lexicographical ordering. But let's think about it for this course as dictionary ordering. So generally, that means alphabetical order. And so I have this set here. I call it S. I started off with a few elements. I notice how the elements are specified in not in alphabetical order, so pear, then grapefruit, then raspberry. We will notice when we run the code that the set rearranges them to be in whatever order it needs. So we're not able to control the ordering of the elements in the set. It's not a programmer-defined ordering. And then to add a new element on line 39, I use this function insert. I don't use push front or push back because that would make no sense. A set doesn't let me control the ordering. I can't add something to the end of a set. So I just use .insert, which is sort of position agnostic. I just add the element and the set puts it wherever makes sense. And then I iterate over the set with a for each loop, just like I would with a list or a vector. And here I have unordered set. An unordered set is basically a photocopy of the set case, except that I've called the data structure unordered set. And recall that the elements are stored in a bizarre arbitrary order, which I'll just say no particular order. So there is something happening behind the scenes that dictates the exact ordering of elements, but it's nothing that we care about nor anything we can really understand from the outside. The elements are stored in an order that makes it very easy for the set to do its work of being able to search quickly. Now, this piece of code I'm showing off in this video doesn't actually show us how we would search a set quickly. I'm going to talk about that in a future video. So here I insert I create the same unordered set as the set I create above, pear, grapefruit, raspberry, and then I insert the value pineapple. And then I print it out with a for each loop. And then finally, here's a vector. So my vector, I create it, we're used to vectors by now. I create a vector with some elements. I can't use push front like I did with a list, but I can use this odd incantation, which we've never seen before. v.insert. And here, I'm telling it where I want to insert the element at the beginning of V. Now, this is something we're going to unpack later in this week's material, which is how exactly is it I can tell a vector to insert at an arbitrary location. And it is this insert function which actually lists support as well. And then I use pushback as we've seen. And then finally, I iterate over my vector with a for each loop. So we'll try running that. And we can see, so we'll just scroll back through. So the contents of L. Well, L originally contained pear and grapefruit. I inserted the word raspberry before the first element, and we can see that means it appears first. And I insert the word pineapple at the end. And so my list is raspberry, pear, grapefruit, pineapple. And notice this is not in any particular order. When I go over my set was created to be pear, grapefruit, raspberry, and then I add pineapple. When I print the set out, notice that it appears in alphabetical order, in lexicographical order, because the set dictates the internal ordering of its elements. Down here I have the unordered set, which was created to be pear, grapefruit, raspberry, and then later I added pineapple. And what I end up with is something... It's hard to tell exactly how it got this out of what I gave it. This doesn't seem to correspond in any way to the ordering that I provided. So pineapple sort of shows up in the middle somewhere. The rest of the elements are definitely not in alphabetical order, but that's because the unordered set, one of the trade-offs we make with unordered sets, is that they get to specify their own bizarre arbitrary ordering of elements, and we don't. And then finally down here with a vector, I was able to insert the element raspberry at the beginning using this call to .insert. We can see there it is, and then I've got pear, grapefruit, and pineapple. Now, I'm just going to show off that if I try doing this, I'm going to run into some trouble. We can see, if I try to use push front on a vector, even though clearly a vector does allow me to insert at the beginning, because I was able to do that with this more general call here, when I try to use push front on a vector, I get a compile error saying, sorry, you can't. There is no push front. And this is a way of the vector hinting at me that although, yes, it can insert elements wherever I want it to, I really shouldn't be using push front on a vector because the vector is not designed for that. And it's the same way that if I tried to use .at on a list, I would have a problem as well. The list would say, sorry, there is no .at. You can get an element of this list with a given index if you do it yourself, but I won't do it for you, as a way of hinting that maybe it's something that's better used with a vector than a list. So in the next few videos, I want to unpack a bit. I want to use each of these data structures for its areas of expertise, not just to show off their similarities.